AP Chemistry Unit 7 covers equilibrium and reversible reactions. It requires deep understanding of chemical reactions, and you'll need to have good algebra skills. Hi there, my name is Jeremy Krug, and this is the place for all things AP Chemistry. You're about to learn the 10 most important things you've got to know from Unit 7, Chemical Equilibrium. If you're new to my channel, welcome. Take a look around, check out my AP Chemistry playlists, that's where the action is, and make sure you subscribe. YouTube tells me that about 80% of you haven't subscribed yet, so what are you waiting for? It's free, and it's an easy way to help out the channel. And if you're serious about getting that 5 on the AP exam, check out my ultimate review packet for AP Chemistry. It's got the full review videos for every unit, complete study guides, practice questions, my tips and tricks for every unit, and 2 full practice exams in the AP Exam Simulator. You can get a free sample today over at ultimatereviewpacket.com. Now, here are the 10 things you've got to know from Unit 7. Number 1. Most chemical reactions are reversible. Reversible reactions are denoted by using a double-headed arrow, while irreversible reactions are denoted with a single-headed arrow. Irreversible processes include the combustion of methane and oxygen to produce carbon dioxide and water, or iron metal reacting with oxygen to produce rust, iron 3 oxide. Another one is sodium bicarbonate, also called baking soda, reacting with vinegar, acetic acid, to produce sodium ions, acetate ions, water, and carbon dioxide. On the other hand, most processes are reversible. For example, water can transition from the liquid state to the gaseous state, but water vapor can also be condensed to become liquid water. Nitrogen reacts with hydrogen to make ammonia gas, but that reaction can also go in reverse as ammonia gas decomposes into nitrogen and hydrogen gases. We can also think about how sodium chloride solid can dissociate into its ions, and likewise, the process could go in reverse where those ions combine to form a solid crystal. Number 2. When a reversible reaction reaches equilibrium, the concentrations of substances stay constant, but the reaction has not actually stopped. The forward reaction simply has the same rate as the reverse reaction, which causes the concentrations to stop changing. Let's take this reaction where N2O4 decomposes into 2 molecules of nitrogen dioxide gas. At the beginning of the reaction, the forward reaction has a very high rate and it slowly decreases as the reaction progresses. The reverse reaction starts with a rate of 0 and slowly gets faster as the reaction progresses. Eventually, the forward reaction rate is equal to the reverse reaction rate. And when that happens, we say the reaction has achieved equilibrium. Remember, at equilibrium, not all of the reactants have been depleted. The products and reactants don't necessarily have the same concentrations. The concentrations have stopped changing because the forward reaction has the same rate as the reverse reaction. Number 3. An equilibrium constant expression, Kc, is written as the concentrations of the products over the reactants raised to the power of the coefficients. Kp is written in terms of partial pressures. Liquids and solids are always omitted from equilibrium constants. Let's say we want to write the equilibrium constant expression, Kc, for this reaction. We take the concentration of the product, NO2, raised to its coefficient of 2, all over the concentration of the reactant N2O4. In the next reaction, we should remember to always omit liquids and solids from the expression. So since there are no gases or aqueous solutions on the product side, the numerator is just 1. In the denominator, we have NH3 times the concentration of HCl. What if we want to write the Kp expression for this reaction? Remember, Kp is written in terms of partial pressures, not concentrations. So we can't use brackets for this one because brackets specifically refer to concentration in molarity. So Kp equals the partial pressure of NH3, quantity squared, over the partial pressure of N2 times the partial pressure of H2 cubed. Number 4. A very large equilibrium constant means that equilibrium heavily favors the products. A very small equilibrium constant means that equilibrium heavily favors the reactants. In this reaction, the value of Kc is 2.5 times 10 to the 47th power. That is an extremely large number. So at equilibrium, we're going to have a lot of product, a lot of water, and very little reactants. Hydrogen or oxygen gases will be present. What about this reaction? This time, we have a very small equilibrium constant, 3.0 times 10 to the negative 18th. That means that at equilibrium, the reaction heavily favors the reactant. We'll have a lot of carbon dioxide at equilibrium, but very little carbon monoxide or oxygen gas present. What about this reaction? This equilibrium constant is relatively close to 1. That means we'll see a fairly significant amount of both products and reactants when this reaction is at equilibrium. And to be clear, very large equilibrium constants are larger than about 1,000, and small equilibrium constants are less than about 1 times 10 to the negative third. Any equilibrium constant in between those values is somewhat close to 1. Number 5. When a reaction is manipulated, K also changes. Reversing a reaction causes K to be taken to its reciprocal. Multiplying a reaction by a factor n causes K to be raised to the power of n. Adding two reactions together causes the two values of K to be multiplied by each other. So for example, this reaction has an equilibrium constant of 0.26. If we reverse the reaction, like this, we have to take the reciprocal of the original constant to find the equilibrium constant of the new reaction. 1 divided by 0.26 is 3.8. What if we're asked to find the equilibrium constant of this reaction? Here, we've taken the original reaction and multiplied all the coefficients by 2. That means we take the original constant and raise it to the power of 2 to calculate the equilibrium constant of the new reaction. That's about 0.068. In this case, we're asked to add these two reactions together and find the equilibrium constant of a third reaction. We can see that the first two equations do indeed add together to give us the third equation. To calculate the equilibrium constant of the third equation, we just multiply the two equilibrium constants by each other. 0.26 times 53, which is about 14. Now, I know the best way to get better at these is to get lots of practice. I actually just added 60 AP-style multiple choice questions just for Unit 7 into the Ultimate Exam Slayer. That's twice what you get on AP Classroom. So whatever you do, keep practicing these equilibrium problems. Number 6. Le Chatelier's principle says that adding something to a reaction at equilibrium will cause the reaction to proceed so that the added substance is consumed, increasing the substances on the opposite side of the reaction. Likewise, removing a substance causes the reaction to proceed so that substance is replenished. Let's say we have this balanced equation at equilibrium. If we add POCl3 gas to the mixture, that means we're adding a reactant. The reaction proceeds to consume that reactant, forcing the reaction toward the product side. That means PCl3 and oxygen will increase while POCl3 will decrease. What if we remove POCl3 gas from the mixture? Well, the opposite will happen. The reaction will adjust to replenish the POCl3 that was removed. So POCl3 will increase while PCl3 and oxygen will decrease. What if we add PCl3 to the mixture? Well, that PCl3 we just added will react with oxygen to form POCl3. So the POCl3 will increase while the PCl3 and oxygen will decrease. What if we remove oxygen from the mixture? Once again, the reaction will proceed so that oxygen we just removed gets replenished, it will proceed toward the product side. So we'll see an increase in O2 and PCl3 and a decrease in POCl3. Number 7, Le Chatelier's principle can also be applied to pressure and temperature. If a reaction is at equilibrium, decreasing the volume of the vessel forces equilibrium toward the side of the reaction with fewer moles of gas. If we go back to the same reaction, but this time we decrease the pressure by increasing the volume, that means that the reaction mixture will have more space to occupy. So the reaction will proceed toward the side of the reaction that occupies more space, which is going to be the side that has more moles of gas. In this reaction, that's the right side, the product side. It has 3 moles of gas compared to only 2 moles of gas on the reactant side. So when we increase the volume, we'll see an increase in PCl3 in oxygen and a decrease in POCl3. If we increase the pressure by decreasing the volume, that means the reaction mixture will have less space to occupy, so the reaction will proceed toward the side that occupies less space, which for this reaction is the reactant side. So we'll see an increase in POCl3 and a decrease in PCl3 and oxygen gases. Number 8. If a reaction mixture is not at equilibrium, we can calculate the reaction quotient Q just as we would K. If Q is less than K, the reaction will proceed toward the products. If Q is greater than K, the reaction will proceed toward the reactants. Let's say we have this reaction in which a mixture of NO, Cl2, and NOCl is analyzed and is found to contain partial pressures of 0.45 atmospheres NO, 0.25 atmospheres chlorine, and 0.30 atmospheres NOCl. As the reaction below proceeds, will the partial pressure of NOCl increase, decrease, or remain the same? We're given the equation and the value of Kp. We need to start by writing the expression for the reaction quotient, which is abbreviated Q. It's written the same way as the equilibrium constant, products over reactants raised to the power of the coefficients. Now, we just plug those pressures given to us in the problem into the expression. We calculate the value of Q, the reaction quotient, as 1.8. Well, since 1.8 is greater than K, the reaction will proceed toward the reactant side. Now, if you have trouble remembering that, use the Pac-Man symbol. Since Pac-Man is eating toward the left, that means the reactants are going to increase. So we'd expect the NO and chlorine to increase while the NOCl decreases. Number 9. The solubility product constant, Ksp, describes how soluble an ionic compound is. The smaller the value of Ksp, the less soluble it is. Ksp is the equilibrium constant that incorporates the concentrations of the ions present when the ionic compound is saturated in an aqueous solution. Let's say we have this balanced equation that represents the dissociation of silver sulfate. For this dissociation, Ksp is 1.2 times 10 to the negative fifth. Using this information, let's first determine the molar solubility of Ag2SO4. Since we don't know what the molar solubility is, let's just call that X for right now. We know that when this compound dissolves, it produces 2 ions of silver. So when the solution is saturated, the concentration of silver will be 2X, since this is a 1:2 ratio. Sulfate is produced at a 1:1 ratio, so the concentration of sulfate will be X. Now, let's plug these values into the equilibrium constant expression for this reaction. As always, it's products over reactants raised to the power of the coefficients, omitting the solid. So this is the expression for Ksp. Now, we plug in the values. Ksp is 1.2 times 10 to the negative fifth. The value for silver is 2X, and that has to be squared. And the value for sulfate is X. So we simplify this expression, and we get 1.2 times 10 to the negative fifth equals 4x cubed. We divide by 4 and take the cube root to find that x equals 0.014. Earlier, we said X was our molar solubility, so the molar solubility of silver sulfate is 0.014 moles per liter. Part B says to determine the concentration of silver ions in this saturated solution. Well, in our original expression, silver's concentration is 2x, which means we take 2 times our x value to find that the silver ion concentration in this saturated solution would be 0.028 molar. Number 10. When solving equilibrium problems, an icebox is an effective way of calculating the concentrations or pressures of substances present at equilibrium given initial values. Let's say we have this problem, in which a chemist places 0.5 moles of hydrogen and 0.5 moles of iodine gas into a 2-liter flask and allows these substances to react. After the reaction attains equilibrium, what will be the concentrations of all 3 substances? We're given the balanced equation and the value of Kc. Anytime a problem gives initial concentrations and then asks for equilibrium values, it's best to set up an icebox, which stands for initial, change, and equilibrium concentrations. The initial concentration of hydrogen is 0.5 moles divided by 2 liters, which is 0.25 molar. It's the same value for iodine. And since the problem doesn't say that there's initially any HI present in the flask, it's safe to assume it's 0. Now this is all that the problem tells us, so we have to use algebra to figure out the rest. We know that hydrogen and iodine will have to decrease. And since they react in a 1-to-1 ratio, the change of both of those will be minus x. The products will have to increase, but it's going to react in a 1-to-2 ratio. So we'll say that HI increases by 2x. Our equilibrium values are 0.25 minus x, 0.25 minus x, and 2x. Let's plug these values into our equilibrium constant expression, which is written as products over reactants raised to the power of the coefficients. Kc equals 50.5. The HI concentration is 2x, quantity squared, and in the denominator we have 0.25 minus x for both of our reactants. To solve this equation, let's take the square root of both sides. So we have 7.106 equals 2x all over 0.25 minus x. We can cross multiply and add like terms, then divide both sides by 9.106 to find that the value of x is 0.195. Now, we can plug that value for x into each of those equilibrium quantities and find that the equilibrium concentration of hydrogen is about 0.055 molar. It's the same for iodine. And for HI, it's 2x, which is 0.390 molar. Now, there's quite a bit of mathematics in these problems, but with some practice, you'll be able to solve equilibrium problems just fine. And those are the top 10, the 10 most important things you've got to know from Unit 7. Remember that if you're looking for even more review and practice, the Ultimate Review Packet has everything you need to succeed in AP Chem. So go check it out over at ultimatereviewpacket.com. Hey, thanks for watching, thanks even more for subscribing, and I'll see you soon.